In this session, I'm going to be talking about why 30,000 foot level reporting is so important as part of a Lean Six Sigma process improvement undertaking. So after completing this module, be able to describe benefits of this form of reporting and why 30,000 foot level reports are needed. Notice that I have a peer review article that was published a couple years ago that describes the benefits of this methodology and the technical reasons why it's solid methodology. Let's talk about special cause variation. Walter Shewhart talked about special cause variation as an assignable cause that could be internal or external to the system. On contrary, Edwards Deming talks about a fleeting event experienced by the system. So to me, those are two different definitions or cases for when a special cause occurs. So this philosophy affects how a process should be tracked. So example situation, there might be new batches of raw material that the process receives daily, or there could be volume in a call center difference by day of the week. Now the question is, should those inputs to an overall process be considered special cause inputs or common cause? So typically what I've experienced is that Deming would say these are common cause, and that's what most people in my training classes would tend to agree with, where Shewhart would say they're assignable and therefore they could be considered special cause. 30,000 foot level strategies align to the Deming philosophy. A couple references here for the charting of addressing stability and also the capability processes described in those two different examples and sections. So basically what we want to do is encourage the most beneficial behaviors. Now we can do that through 30,000 foot level reporting, and the objective of 30,000 foot level reporting is not to control the process. 30,000 foot level stability assessment's conclusion can be quite different from a traditional control charting assessment, whether a process is in control or not. Now, the advantage of 30,000 foot level charts can be used to baseline and demonstrate improvement that was made through a Lean Six Sigma project. I cannot count the number of articles and papers and presentations that I've seen that say that they've made all these improvements, but they're not showing me really in a simple format of how they really improved a particular metric from executing this project. And that's what the 30,000 foot level report adds to this whole Lean Six Sigma project execution roadmap. A lot of times we'll blame executives or leadership and management saying they're not listening. Well, I think if we went in and showed them how we really make an improvement to key performance indicators that they had, then they'd be able to understand the value that we bring to the table as a process improvement practitioner. So what I really have is 30,000 foot level and 50 foot metrics. 30,000 foot level metrics is what I'm going to be focused on here. Control charting, that sort of thing, would be at the 50 foot level, where you're really trying to control the process. So at the 30,000 foot level, we're tracking a measurement over time. It can have a mixture of machines, it can have a mixture of people, it can have a mixture of days of the week. It has a lot of different components to that. And we then see how we're performing, and then we compare to customer needs if we got specifications, and then decide that we might have a problem or we want to improve it. So that pulls for the creation of a Lean Six Sigma process improvement project. If we did a good job, then that metric transitions to new enhanced level of performance, and then we can describe the benefits of what we got in terms of monetary gains, if it's appropriate. Now, this is how you'd approach a situation where you have a continuous response. If you got an attribute response, you wouldn't do the probability plot. Now, if you look at traditional control charting, this is the kind of decision tree that you might have to determine what kind of charts that you use for a particular situation. However, we can go in and have different signals. You comparing the 30,000 foot level to a traditional X bar and S chart, for example. So in this case here, what we really don't have is the variability between subgroups as far as affecting the control limits. And that's not much different than the talking about raw material lot-to-lot variability that occurred between each days. We thought it should be common cause. Well, the chart on the left doesn't address that as common cause, but a chart on the right does. So you can see that there can be a dramatic difference in what a response looks like. Now, why is this discrepancy exists between X bar and R charts and the 30,000 foot level charts? Well, the 30,000 foot level uses an individual's chart to actually calculate the control limits, where an X bar and R chart uses a relationship as shown mathematically here. Now the difference is that for the X bar and R chart, the variability for the control limits is determined completely within time zone variability. So it's within subgroup variability, where on the individual's chart shown below, it's the moving range. Therefore, since that moving range is between adjacent subgroups, then we can capture the variability between time series events that we are subgrouping on. We have some other problems with the process capability indices, which is popularly in Six Sigma. It seems like a very simple relationship, upper spec limit minus lower spec limit over Six Sigma, but the question is, where do you get standard deviation or sigma? Well, in this slide, I'm showing 6 different methods on how do you get it. How do you determine what it is? And it depends upon if you got an individual's chart, if you got a X bar and R chart, the results can be dramatically different. So what we want to do is get around all this. So the way we do that is through a 30,000 foot level chart, which basically has 2 steps. The first step is we want to assess process predictability. In other words, we want to see if the process is stable from a high level point of view. The second point is if the process is considered stable, we want to create a prediction statement. We would create this prediction statement by considering the random sample, considering the data from the recent region of stability random sample of the future. So as in 2A, when there is a specification, we report the nonconformance rate or defects per million opportunity rate. B, if there's no specification requirement, then we say we got to look at the median response and 80% frequency current rate. I'm showing you a few charts here, but I'm going to be covering these charts in more detail later, but I wanted to give you an idea what the 30,000 foot level chart looks like. So for this particular case, the chart on the left says we got a stable process, and therefore we can then consider that to be a random sample of the future. We then create a probability plot. In this case, we're going to have a specification. We will pull off the median value and the 80% frequency currents are 90 minus 10 rates. So that's what we'd have if we had no specification. If you got a specification on the probability plot, then you would come up from the x-axis at those specification limits and determine the percentage that are beyond those values on the upper side and the lower side. Now, as I mentioned earlier, we want to see the magnitude of improvements that we made from improvement projects. So this slide demonstrates how that can be done. This is actually the actual data from something I looked at a number of years ago. But now we see that we got a current process and the median is such and such with 80% frequency occurrence shown there also. We can also take out the outlier value and consider the ones that are not, on the 8 or so that are beyond the red point, then those are data. That's data for determining the common cause variability. Now, sometimes we might have multiple samples in a subgroup. And if we got a specification, then we might get a chart look like this. So instead of an X bar and R chart, we use an individuals chart of both the mean value within subgroups and the standard deviation. Now, sometimes we might need to take a transformation of the standard deviation, and because the value cannot get below 0 standard deviation, obviously. So in this particular case, when we looked at it, it came out an estimated non-conformance rate of about 0.34%. So if we have a 30,000 foot level report out for an attribute situation, we don't have a probability plot, but we simply read the average value off of the y-axis, assuming we didn't have to do a transformation to create this chart. So in this case, we got a predictable process of about 0.231. Now, in both cases that we've had, if you don't like that answer, then you've got to do something to improve the process. You don't go in and ask the question, why is one value low and one value is high? You look at the data collectively and build hypotheses. You might ask, why is there different, or could there be difference between machines, operators, different facilities that's doing the same kind of work, so on. That can give us some insight to what we might do differently. I'll be making reference to the IEEE project execution roadmap. This is found within the project execution guide and also IEEE volume 3 in the back. This chart is used to determine if the process is stable. And then this chart is used to determine the process capability if the process were stable. This is an example when you didn't have any transformation. See how we're bounded by 0? Maybe physically you can't get below 0 for this particular process. Notice how we've got a curved probability plot. That's indicating that we need to take a log normal distribution transformation. Now, if we got zeros in the raw data, then the thing we had to do is shift to a certain value, and then we take a transformation on that value. So if we did that, then we put the specification on there. Now it follows a straight line with the log normal plot to it, and we get a better estimate of our non-conformance rate. So we did, this data is from a coin toss exercise in the class where we threw the coin against the wall, measured how the distance that the coin settled at after the throw. And we noticed that we had a log normal distribution, which is kind of obvious because the ball acted as the lower boundary. Sometimes people want to look at all the data. So they take all the data and plot it out, and they'll find out that they have a lot of out of control signals. The reason for this is that the variability for the control limits is calculated from the adjacent the variability between adjacent values. So in this case, if you took measurements real quickly, then the thing is you might have autocorrelation, or the data point that you're measuring now is dependent upon when you're done frequently. You can get charts that look like this. Where if we started asking people, do you think you might have differences within the day? And if they say yes, then we want to subgroup it by day. So this is the same data. The only difference is we're subgrouping by day. Now we see got a stable process, and we can make a prediction statement. The median is 298, and 80% of the values are between the two values shown. This is an example 13.1 of where you have a report out, and now we have a particular failure rate that's shown. That's a stable process. Again, if we don't like the answer, then we got to change the overall process. And proof of the pudding that we made a difference is the individuals chart transitioned to a new level of performance. This is a comparison of a traditional P chart to a failure rate that we'd have from the IEEE scorecard. As you can see, the conclusion is quite different. And the reason for that is that the variability between subgroups has nothing to do with the control limits. However, if we go in and use an individuals chart, the 30,000 foot level approach, we notice that we got a moving range value, and therefore that situations occur, and we get a quite different picture of how our process is performing relative to stability. So in this module, we learned benefits of the 30,000 foot level reporting and why 30,000 foot level report outs are needed.